So if we overview, this is overview of the various different control charts. So the SPC has a host or a collection of control charts you can use based on the underlying characteristics of measurements as well as the statistical distribution associated with those measurements. So largely we have the control charts for the variable measurements. If you remember, for the variable measurements, we are measuring quality dimensions as is, right? If it's the weight, we're measuring in terms of ounce. If it's the length, we're measuring in terms of millimeter or other units. If it's time, we are measuring using the second or things like that. Where in the attribute measurements, we are measuring things in 1 or 0 fashion. Okay, so mostly we are relying on different statistical distribution to detect whether system is in control or out of control. So for today, we're only going to focus on the variable measurements. There are 3 different types. X bar and MR charts, X bar and R charts, X bar and S charts. So they all are made up by 2 different charts. Okay, you see the R charts first, or then you see the X bar charts second, or things like that. These are pair of control charts instead of just one control chart. The difference between them is their differences are built based on the sample size. So if your sample size is 1, you'd like to follow the X bar and MR charts. If your sample size is less than 10, you need to use X bar and R. And sample size is larger than 10, you need to use the X and S charts. The underlying reason is that the estimation for the standard deviation is going to be very, very different when you have different level of sample size. So for example, the sample size 1, if you think about the standard error formula, standard error formula is square root n and square root n and standard deviation, right? So if sample size is 1, you're basically talking about the population distribution, right? If it is too small, sample size is too small, in that case, the traditional way of calculating standard deviation might not be very, very efficient. Okay, therefore, we need to use some workaround to estimate the variations. And when you have a larger sample size, it makes the estimation of the standard deviation easier. Therefore, we follow different approach. So difference here is the sample size. Okay, that's all I want to emphasize at this point. So here is a prerequisite, and I hope you can solve this by yourself at this time. Okay, please plot the population distribution and the sampling distribution in the same space. So parameter here is here. I gave you 3 parameters. I'm asking you to draw population distribution and the sampling distribution in the same space, meaning here is average, mu equal to 1, right? I want you to plot both population distribution as well as sampling distribution with a sample size of 9 here together at the same time. Please pause and think for a second. See if you can handle this question yourself. Okay? So since average is here, right? 1 standard deviation, 4, 2 standard deviation, 7, 3 standard deviation is 10. Again, here you are seeing -2, -5, -a in here. I hope I'm right here. Okay, so you see 9 here, 9 to the right, 9 to the left. So if you're plotting the population distribution, it's going to be something like this, so that you only have a very small percentage spread it in 2 end. Okay, so less than 0.3% will be concentrated here. You need to draw sampling distribution. In other words, if you repeatedly draw sample of 9 from here, from this population here, sorry, let's make it prettier, and then what would that distribution is going to be like? Regarding the difference, I have explained the difference in the video that I have posted over the weekend as I try to explain the homework number 3. If you do not understand the difference between population distribution and the sampling distribution, I warn you, stop here and go back and review those concepts. Okay? If you do understand, you come to me. And then you come back to this video and you proceed. Okay? And we draw sample of 9. That makes standard error become, which is 3/3, which is 1. Okay, so standard error is 1 in order to plot the sampling distribution of the average. This is 2, this is a 3, here is a 4. Okay, 0, -1. These are 3 standard deviation range. Again, you want to give a little bit beyond 3 standard deviation. You'd like to draw something like this, so that you only give a little bit of dimensions outside of the 3 standard deviation range. So here, blue one here, it's a story. It tells you the story about the sample average. Okay, the red one here outside will give you the information about the population. Hope that makes sense to you. So this is very, very important to understand. Okay, so if you think about that, if we are relying on the sample result to determine whether the process is in control, out of control, which population we should be relying on to make the decisions. Okay, if you thought about its sampling distribution, right, and then you are correct, because we are drawing sample each time and then using the sample information to inference whether the process actually in control or not in the control, it's out of control. In that case, we need to rely on the sample result. Therefore, we need to rely on the sampling distribution. Okay, so whatever discussion we are doing from this point and forward, we are doing the discussion using the sampling distribution. Okay, there's some other discussions. So the first thing, the control limits are not specification limits. The specification limit is the voice of your customers. The control limit is just the control limits. Okay, something may be falling outside of control limits, but it may still meets the requirement or demands of the customers. Okay, so control limits, in other words, it's manufacturers' self-imposed limits to detect outlier from their manufacturing process. I hope that concept makes sense to you. Okay, so a lot of times this is our control limit. Our control limit is here, and we'd like to make the specification limit as far as possible. So sometimes you do make some mistake here. Sometimes you do see some parts that are falling outside of the control limit. Once you see something outside of control limit, they give you a reason to stop the line to re-examine what is wrong with the process. But it does not help you to re-examine the specification limit. Specification limit wise, you do need to reevaluate that anymore, because that is a hard limit, right? Determined by the customer's demands and requirements. So specification limit and control limit are 2 different concepts. Okay, and again, process capability is no longer the primary concern in the process control. Okay, we have already taken care of all these things up front. Okay, you compare your process capability with the customer specification limits. Okay, you already have a pretty good idea that our process is capable of meeting the specification limit. Control limits are only used to detect whether your process is actually functioning as expected or not. Okay? Again, the control limits are the function of sample size. So this is a control limit, right? This is a 3 standard deviation control limit. Again, because of standard error is a function of sample size. Therefore, if we're using different sample size, you will be seeing different sampling distribution. That is the reason why I'm saying here, control limit are the function of sample size. The same process with different sample sizes will require different control limits. Therefore, as long as the sample size does not change, same control charts will remain useful. Okay? However, here are some cases you need to think about. Even the process is in control, there will be still some small chances that a point will fall outside of the limits. The chance is very small. It is 0.3% small. Okay, so occasionally you will see that a part will be falling outside of 3 standard deviation here, but that can happen sometimes actually, but the chance is small. And the process of out of control, there will be still some chances that a point will fall within the limit. That means even you're seeing some of your observations falling within your control limit, that could be still, the process could still have a chance to be out of control. Imagine that if you're seeing, it's getting messier here, but imagine if you're seeing, this is a changed process, right? From here, change to here, meaning the average has increased, right? But if you did not detect the change in average, it will give you, I think a lot of times it will give you the parts in this range, right? In this case, you'll be seeing a lot of observations falling your control limit, but in fact, the process average has shifted. Okay, let me maybe give you a better drawing here. You're expecting this, right? But it has changed to this. Okay, this is new process, which is bad process, but a lot of times, more than 50% of time, right, it will give you outcome falling within this range. Okay, so in that case, if you are using the control chart that is established based on this distribution, you're still thinking, my process is still within control. But that is the dangerous type 2 error. Okay, you are accepting the false parameters. Okay, you're accepting false parameters. You're not stopping line, even though it has gone out of control. So that is things you can think about when we talk about the control charts. So I will stop my video for here before I move on to the more technical part of the control charts. It's mostly involved, this mostly talks about how to construct a control charts based on the different sample size, and then the solution on Excels. Okay, therefore the next 2 or 3 videos is going to be very, very Excel intensive.